All right, for the last week of class here, we are going to switch gears a little bit, and we are going to investigate something known as simple harmonic motion. And what we want to focus on, we want to focus on objects where the motion that the objects are displaying, the motion regularly repeats, or that is, the motion is periodic. So we've sort of seen things like this previously, an object going around a circle, so some uniform circular motion problems that we've looked at. Another way to think about these things is to describe the periodic nature of the motion. And so to do that, we're going to introduce a few new terms. First off, we want to just remind ourselves the definition of frequency or period. If motion is periodic, it means that the motion repeats over a certain amount of time, right? So every second or every minute, the motion repeats, and so the frequency is defined as 1 over the period being how long it takes for that motion to happen. So the unit for frequency is the hertz. That's an inverse second. And remember, there's like a revolution or a cycle as sort of a placeholding unit in the numerator here. So this is like a cycle per second, or a revolution per second, depending on what type of motion you're describing. So frequency, 1 over the period. Now, for simple harmonic motion, this is motion that repeats, and it's motion that repeats because the net force on the object is proportional to the displacement of the object. And so I've got an example here, the example being a mass attached to a spring on a frictionless table. So if I take this mass on the spring and I pull it out to this extended length and let it go, obviously the mass is going to get pulled back to the left. And so as it moves back to the left, it's going to pass through the equilibrium point, and then it's going to continue this way, and it's going to reach some furthest displacement on this side where the spring is compressed to a maximum amount, and then it's going to go back. And so this motion is just going to repeat, and what we want to do is we want to come up with a way to characterize or quantify the position, and then from that the velocity, and then from that the acceleration of our object that's undergoing uniform circular motion. All right, so that's our goal. And so we're going to start with just the position of our object. So again, this is my mass here. It's moving back and forth, right? So there's the periodic motion. So the position changes with time. Now, how does it change with time? Well, it changes with time periodically, or with this trig function, cosine of, and then the argument would be 2 pi over the period, which is known as the angular frequency, and then multiplied by the time. And so a cosine omega t is a way that we can describe the position of this object. And so if you look at t equals 0, when you plug in 0 here, you get a position of a, and that corresponds to the amplitude, or the maximum displacement. So I pulled this mass out to the right here, and then I let it go, and then it's going to swing in, it's going to swing back. And so as time goes on, this function right here will tell us exactly where the mass is located at any point in time. And a few better figures to check out in the book are 15.5 and 15.6. If you were to plot the position as a function of time for this motion up here, you would end up getting something that looks like this. So this is basically the cosine function. And you'll notice that if I just if I shift this curve a little bit to the right or a little bit to the left, then I can get what essentially looks like a sine function, or a version of a sine function. And so you can shift the pattern just by adding what's known as a phase inside the cosine argument. And that should make sense because, remember, the sine and the cosine functions are just shifted 90 degrees out of phase with each other. And so adding a phase angle will just shift the function left or right, or shift the curve left or right. So again, this is the position, and if we want the velocity of our object undergoing this motion, then we should just take the derivative with respect to time of our position function. So if we take the derivative of this function, we just get minus, because the derivative of the cosine function is minus sine. And then we'll have to use the product rule, so we'll also have to take the derivative in here, which the derivative of omega t is just going to be omega. So we end up with minus a omega sine omega t plus phi, which the book writes out in this form with Vmax, where Vmax equals the amplitude multiplied by the angular frequency. And then if we want the acceleration of our object, well then we're just going to take the time derivative of our velocity function. And so let's take another time derivative of this function. Well, that's going to give us derivative of sine is cosine. So we've got cosine now. Now we still have to do the chain rule, so we'll have to take the derivative of omega t. So we get another factor of omega. So we had a omega up here. Now we've got a omega squared. Still have the minus sign left over from up here, but now again it's cosine. And again, the maximum acceleration then is just this leading term, the amplitude multiplied by the square of the angular frequency. All right, now in the previous portion, I was talking about a mass on a spring, but I didn't actually plug in the specific values that are associated with a mass being exposed to just the spring force. And so now we're going to do that. So we're going to look at this. The spring force, Hooke's law, is that the force is proportional to the displacement of the spring. And so, and then this negative sign corresponds to the fact that the force is in the opposite direction of the displacement. If I stretch the spring this way, the force will be restorative, it'll go back to the left. If I compress the spring this way, then the spring will be pushing out to the right. So that's the significance of that negative sign. Now, since this is the only force acting on our object, or the net force is really all that it needs to be, then our net force has to equal our mass times acceleration. And acceleration is just the second derivative with respect to time of the position function. And so we end up with an expression right here that relates the second derivative of position to the position function itself. And so what I'm going to do is I'm going to take the expressions for position and acceleration from the previous segment, and I'm going to just plug them in to this expression. So I'm going to take two derivatives of position, which remember is the acceleration. So here is the acceleration from the previous page. And then on the right-hand side, I'm just plugging in the position. And notice both sides have an a, both sides have a cosine omega t, both sides have a negative sign. And so omega squared has to equal k over m. So omega has to be the square root of k over m. Remember, k here is the spring constant, right? So it's specific to the properties of the spring that you're using. So the angular frequency for this simple harmonic motion is going to be dependent on the spring that you use and the mass that's undergoing the simple harmonic motion. Now, omega is related to the period, so you can get the period by just switching these terms. So the period is 2 pi times, and then this is inverted, the square root of m over k. So the angular frequency, the period, and then the frequency is just the period, is just the angular frequency divided by 2 pi. And so take omega divided by 2 pi, and you get the frequency. Now, another thing that we want to consider is how can we describe the energy of the object as it's undergoing simple harmonic motion. And so, right, there's, if you think about this, we, to start the motion, maybe we'll bring the block all the way out here, and then we'll let it go, and it'll swing back and forth, oscillating. And if there's no friction, it'll just oscillate back and forth forever. And we want to know, well, how can we describe the energy as this thing is oscillating back and forth across the table? Well, the total energy is just going to be the sum of all of the potential energies and all of the kinetic energies. And if we pick our table to be at height 0, then we won't have any gravitational potential energy, but we will have some spring potential energy, right, depending on how much the spring is compressed or stretched. And we will have some kinetic energy because the mass is going to be moving. And then we want to remember that our position for simple harmonic motion and our velocity for simple harmonic motion, we can just plug these right into our expression here. And so that's what I'm going to do. So I'm going to take this, plug it right in here, and now all I'm going to do is just move around some of the terms. So still have the cosine squared term, still have the sine squared term. You'll notice that I've squared both a and omega got squared. M stays out front, so it's not squared. Now I'm going to plug in for omega. Remember up here, omega is the square root of k over m, so that means omega squared is just k over m. So still have cosine squared and sine squared. Now what I'm going to do is notice that I've actually got m and m here. So I've actually got 1/2 ka squared, 1/2 ka squared in both terms, so I can factor that out. And I still have the cosine squared plus the sine squared. Well, that turns out to be equal to 1. Right, this is equal to 1. And so the whole total energy expression works out to be 1/2 ka squared, where again k is the spring constant and a is the maximum displacement, the amplitude of the oscillation. And so something really interesting is going on here. This is the total energy at any time, right? At any time t, what's the position, what's the velocity? And as we plugged in the values and moved things around, we got that the total energy at any time, doesn't matter when, is just equal to 1/2 ka squared. Those are all constants. So the total energy, and this shouldn't be surprising, the total energy of the system is constant. It doesn't matter if we are all the way out at the edge when we're not moving at all, but the spring is stretched the most, versus moving right through the middle where the spring isn't compressed at all, but the velocity is the largest. And then down here where it's compressed the most but not moving anymore. At any of those times, the total energy remains the same. So it may be that all of the energy is potential, or all of the energy is kinetic, or some in potential and some in kinetic. But when you add it up, you always get the exact same amount, right? The same total amount. And if you want to know what the total energy for your simple harmonic motion mass on a spring is, it's 1/2 k a squared, and again, a being the maximum displacement. So you can rearrange these terms here to solve for the velocity at any time, or the speed at any time, and that would be this expression here. So depends on the total energy of the system, and then depends on how much the spring is stretched or compressed at that given moment. If the spring is not compressed at all, so if x is equal to 0, then that's the maximum velocity that the object can have. And then at some point, the compression or the stretch will be equal to the maximum displacement, and then this will be 0, and the speed will be 0, right? So those are the ranges of values that you can have for the speed.